Oh yeah, as James said, I'm going to be talking about programming Crossroads with overlays and how they can potentially help time to solution. I've got a very distinguished set of co-PIs and PIs that are working with me on this, and so they're listed here. And obviously, we acknowledge and are very thankful and appreciative of the generous support from Intel and VMware to support this work. All right, so going back, I think those of you who've seen any of these these talks before, this is the overall Crossroads effort. This is what Intel and VMware had sent out a request for proposals, and we responded to. But fundamentally, there's 5 research vectors. The research vector one is essentially applications. We're looking, what we proposed and what we're working on is machine learning analysis, microservices, and network functionality. Basically these applications, the intention is that we can run them on a variety of different hardware platforms. But in reality, what we're really focused on is really going and looking at this 3D FPGA that's going to have essentially an FPGA fabric along with a base die which will have hardened logic and storage and memory and interconnect, right? So fundamentally, we're looking at running these applications on this new FPGA that we're looking to define. And the components that feed into this is overlays is what I'm going to be talking about. Kind of place and route is something that Von Betz and David Pan are working on, and then the dynamic runtime, which is basically partial reconfiguration and so on that James Ho has been working on. So let's start. This is kind of the high level overview. So, effectively, to get a little bit more into this whole base die idea, right? Really, fundamentally, we all know that FPGAs are phenomenally good at configurable logic that needs to change. But, in reality, there's a bunch of things that don't need to change. And, we need to, ideally, we have hardened versions of those which kind of remove the FPGA, the inefficiency of FPGA that are there for the ability for us to change them. So, the things that I said that could be there, memory is the first thing that we're looking at. Clearly a NOC, that would allow us to move data around, to teleport data from one portion of the FPGA to another. Accelerators, we're going to be looking at specifically, processor support for the overlay work. But fundamentally, we're looking at designing and, through a lot of studies and research work, really this kind of new, kind of FPGA. And so really, we're looking at how to evaluate these, how do we, figure out what the right fabric die architecture is, the right base die architecture, how we're going to connect them connect the two together. And, how do we need to build something very specific for each kind of application space, or can we build something generic down here and have all of the differentiation, kind of be built up here? This is really kind of one of the fundamental components of this particular center and the research we're doing. So going back to overlays, fundamentally, if we take a look at these FPGAs, and not just these 3D FPGAs, but standard FPGAs, fundamentally, and if we step back from it, our real metric of goodness is time to solution, right? And what do I mean by that? And we also should say cost to solution as well. Time to solution doesn't matter if it costs too much, but fundamentally it's this time and cost to solution is the real metric of efficiency. And this really starts from, kind of conceiving with what we need to do through the development, debug, deployment, and the runtime of all of the runs that you need to run. So for example, if I decide that I need to solve one specific problem, I need to go and design, a new car engine, right? The kind of, the time to solution is, me figuring out what kind of computational resources I need to do this, all the way through architecting. Maybe I decide to write this purely in software, run it on Xeon processors, or maybe I decide to go and build a hard, an accelerated component in an ASIC, whatever it is. I take all of that to the time that I get all the results I need to design that new engine. That's really the time to solution and the cost to solution that we're looking at, right? It depends on the solution and different timescales. Sometimes I just, if I'm just writing a little script to kind of process my latest sprint build to see whether or not it's correct, I might, that's something that I might just write a little Python script or Perl script to do. But, and I might not even think about doing hardware acceleration. But if I'm doing something that's really long term and that's going to take, that could potentially take a long time, I can, the different kinds of potential solutions kind of open up, right? And sometimes I won't even start the problem if it's too long, right? There's no point in trying to predict the weather 2 days from now. If predict the weather, if my weather prediction takes 2 days and I'm trying to predict the weather for tomorrow, right? So there's going to be a lot of, we as engineers trying to solve problems, we have to take a look at really see what's possible and the direction we should take. FPGAs have traditionally very fast deployment and runtime, but traditionally not a very fast in development and debug, right? And so that's kind of the problem that we're trying to address. So can Crossroads FPGAs lead in time to solution, right? Can we actually get a better solution, a better time to solution than anything else? And that's what we're trying to do. It requires really software, higher level language. We actually think that the way we program a lot of our software is actually too low level and could be improved. We need to be able to do very fast compile times, right? One of the problems that, I've seen, many times with both my students and at Microsoft is, this develop and debug cycle is actually quite long, and it has a lot to do with those compile times. Debug visibility is something that we really want to be able to introduce into this process, and ideally we can be better than what software offers today. We want to be able to be quickly adapt to runtime requirements. So, in the beginning of my development, I'm going to be more focused on debugging, the application, the algorithm, and so on. But over time, I may need to, go to higher performance, and I might be resource constrained at certain points where, I don't have enough FPGA resources or whatever. I want to be able to quickly adapt to whatever the requirements are at the particular time that I'm of the development of the total time to solution cycle. I also want to be able to call other hardware. I don't want whatever I'm doing in my FPGA to only have to rely entirely on the FPGA. I want to be able to call out to CPUs, offload to a CPU, complex operations. I want to be able to call ASIC components and so on, while maintaining high performance and power efficiency. Right, this is kind of the high level goal. And so the solution's got to be some mix of specialization and generality. So what we're trying to do is we're trying to provide a framework in which we can go do heavy specialization, but also have enough generality so that we can get a better overall time to solution. So if we look at our traditional programming of FPGAs, I'm sure that most of the audience are real experts here. So I'm not going to spend a whole lot of time on what we do traditionally, but we all know that we go and figure out what the workload is. We go and architect a solution. We write our RTL and we go through synthesis, place and route. We generate this specialized circuit. It's not general purpose at all. We generally get the best performance this way. It does require a lot of hardware expertise. It requires a lot of development time, sometimes years, not just weeks and months. Compile times take hours and sometimes days. And it basically, although we can go and factor things, we can optimize very aggressively. This has to be done in the context of the RTL that we have, right? Porting is, if we need to move to the next generation FPGA or so on, it's okay. But still, a lot of times there is work to be done. Even if you port to a different FPGA in the same family, there's oftentimes some work to do done. And there's no dynamic specialization of this path. If we go and look at the high-level synthesis, right, basically we are able to improve things, especially in the development time. We can go down to days and weeks, but performance is often quite good. Maybe not quite as good as RTL in some cases, but often quite good. And we can do more factored optimization, meaning that we can go and take pieces of this and go and match it up with other components. But only in the HLS system itself, right? Core portability tends to be better, and you can run this, purely in software. So what we're proposing to do is actually go and look at overlays as a potential solution. What we're doing here is we're really essentially building a processor in FPGA. This is a specialized processor, but a processor nonetheless. So it goes and fetches instructions. You program it, by going and writing it some higher level language, and then we go and essentially compile those into instructions that then get loaded into the instruction memory that's in that overlay that's implemented on the FPGA. So you basically have a software development pipeline up here. This is exact. There's no real fundamental difference here. But here, by putting in the correct functional units, the correct data types, the correct data paths, and so on, we believe that we can get a lot of efficiency out of it, which is normally not seen if you just go and do a general purpose processor on the FPGA. right? And so we believe that on these metrics, we do a lot better. The one area that we're, potentially not as good in is going to be in the performance area. All right, so why overlays on FPGAs? So if you look at kind of the two general solutions that people approach, kind of flexibility in silicon. One is as an FPGA where we can go and reprogram at the circuit level. And what a lot of people do then is they build a highly specialized circuit to go and execute that particular function. And when you do that, it's extremely efficient and you optimize away anything you don't need, right? And there's certainly no instruction fetch unit, for example. The other approach that people tend to like to use is an application-specific processor that they implement in an ASIC. So you go and build a highly specialized processor, but it's going to be in an ASIC. And so all of the, the circuits are optimized, but you still have to build in that interpretation, right? That instruction fetch unit and so on. So that all is, that all winds up costing us quite a bit. But we only pay the inefficiency at one level, either at the circuit level or at the instruction level. We don't pay it in two. So if we do an overlay in FPGA, we pay them both. We have to pay at the circuit level and we have to pay at the instruction level, right? So both of them, wind up becoming expensive. So the reason why we think overlays on FPGAs are useful is because in a lot of cases, these overlays can change slower than the application changes. We have to go and do debug, the application changes. And so we believe that, by going and building an overlay, we can make that development and debug cycle much, much faster. And you can go in, by going and building overlays correctly, we think we can, we can actually build in some debug capabilities that aren't present in a standard application-specific processor when we use HLS. We can change faster than the silicon be designed. This is in addressing the ASIC. I mean, ASICs take a long time to develop. I mean, if the fastest that, people tend to claim is 1 year, 5 quarters, but this is kind of the TPU from Google. They claim 5 quarters, but you also have a deployment issue. Actually getting those parts into the data center, ramping them up, getting them all, wired up and everything, that takes time too. Right. And so fundamentally, if you look at the entire time it takes to get your solution done, you're probably adding at least a couple years if you're going to be using ASIC. So that's fundamentally there's a lot of time that's potentially wasted there, as opposed to FPGAs that are already deployed in the data center. You just go and load the new overlay as you need it, and the new programs much more often onto those overlays. So we believe that this is actually going to provide us a better time and cost solution. Yeah, we believe that FPGA specialization can overcome the 2 layers of inefficiencies. And we have many examples of this, right? So Brainwave from Microsoft is an example where we're actually, we were able to demonstrate and actually roll to production, cases where an overlay on FPGA is more efficient than a GPU or anything else that we were able to compare against. And we have some internal Microsoft projects that show how this kind of overlay technology does much better than we can on standard programmable processors. And there's work that my team has done at UT when the PDL FGPU, where we showed that an FPGA overlay can be competitive with a hard GPU. So what this does is really incorporates FPGA advantages: small memories, lots of bandwidth under user control, specialized data types, and specialized data movement. Right. One of the things that is really talking with many people. One of the things that FPGAs have real advantage of is they go and instantiate a huge number of small memories that have a tremendous amount of bandwidth. So if you look at a Stratix 10 Agilix part, they have on the order of 100 terabytes per second of bandwidth. There's no processor out there that is kind of at that level. Certainly not general purpose processors. You have to get into very application specific, and even then, what winds up happening is that bandwidth is fairly general. It's 32 bits wide or 64 bits wide, in ways that are not necessarily well mapped onto the application. So why we think this all will work? We started. I did this project back in 2002 with my first company out of grad school. We called it Magilla. I took it out to UT after the company stopped working on it. So, but fundamentally, back at my first company, it's called Avici Systems. We needed a 40 gigabit per second network processor. And the competition was designing their own. They were building specialized processors. So Cisco at the time, we all knew what was going on, even though this wasn't public at the time, but now it is. You can look it up. Their Toaster series of processors in this time frame had 188 to 192 Tensilica cores. They're very difficult to program, right? So we knew that trying to go and use this particular set of cores to do to do network processing was very difficult. So, but they were able to achieve the performance, this 40 gigabit per second. So we started actually with an Intel IXP 2800, 2850 network processors. We had a lot of meetings with Intel. They were very excited about this. And those network processors were designed to run at 10 gigabit per second. They were running at 1.4 gigahertz. This is actually in the time of the Pentium 4. So the frequencies that we were seeing from these cores were basically the same as what the state-of-the-art frequencies were from standard cores. There were 16 cores in the 2800, 2850 part, and there were roughly 900 instructions per packet. It's 25 million packets per second. It was very hard to get to work at to actually meet the 25 million packets per second performance. We were able to get it to work only when we started programming it as a piece of hardware rather than as a piece of software. Intel originally suggested we treat it as pool of threads, meaning that each packet was assigned its own thread and you would just run to completion. But it turns out that the various contention we had within the processor wound up really making it very difficult to meet performance. It was fairly easy to get 80% of the performance. It was very hard to get to the 100%. So what we stepped back and said, look, we had originally designed 9 ASICs and this startup company that I was at, we didn't have enough funding to build another ASIC. So we went and said, hey, can we build this network processor in the FPGA that was competitive in performance, power, and easier to program at the same time? So we were able to go and effectively build a 100 million packet per second network processor for core router in a single Vertex 2 Pro. So we were Xilinx house at the time. It was basically one packet per cycle, ran at 133 megahertz to give us a little bit of headroom. It's very, very predictable performance. There's actually no need to simulate, and relied on a few things: that the application code was written by network experts calling identified functions. We had highly tuned functional units written by RTL experts that implemented those functions. And we built a tool that combined the two into a single point piece of Verilog that implemented that functionality. And then any changes to application code, however, resulted in changes to the Verilog and required a recompile. Right, so essentially what we're doing, you can think of as a high-level synthesis. What's dividing it between, actually three main components, really fundamentally the application, these functional units that would support that application, and essentially a skeleton that kind of, you can think of as a microarchitectural framework in which all these things fit together. And that included a finite state machine that would be running, this particular processor, or this particular hardened, a hard circuit for that particular application. So the functional units are the key resource, right? That's the key resource that we're trying to maximize utilization for. It's hand-tuned IP, as I said. We generally try to get throughput of 1, as much as possible. And then we wrote in sequential code, right? Sequential C grouped in what effectively what are VLIW blocks, each consisting of some sort of pre-data, so pre-functional unit kind of processing. We would go and call libraries, which would be these functional units, and there would be no dependencies between the calls in a specific block. And this is really just to simplify the hardware. Rather than having to try to figure out what the dependencies are dynamically, we just assume that there weren't any and that the programmer would take care of that. And then we process the results. We call post-functional unit. It would be some combination of logic, and then a computer branch at the end. So here's a very, very simple example of the code. I've got all of the registers are basically all of the variables that I created before. These include the initial packet that arrived. And then basically I would go and generate, some sort, these, various, intermediate pre-functional unit kinds of parameters. Then when I would go and call my functional units, I have in this particular case 4 functional units, and I call them with some set of the inputs that I computed, and also I can use registers that I had before. I don't have to necessarily go. These are variables that I computed in the past. And then what I would do is I would go and then post-process and then kind of write back to the particular registers that I want to keep. And then I would have a computer go to the next block, right? So fundamentally, this was the code that the microcoder would write. And if it's really just C, I mean, if the tooling was good enough that fundamentally it would look like C and operate like C to the programmer, you could go and essentially go and by providing the pre-FU functions in a C function, and each one of these functional units in a function, you could just go and compile this as a piece of C code and effectively run that way as well for debug and development purposes. So one thing that we assumed is each VLIW instruction completed before the next VLIW instruction in the same thread started, right? So we can multi-thread across many different threads to improve the efficiency of the hardware that we developed. So basically what happened is the original Magilla Gorilla++, so Magilla was the internal name at my first company. Gorilla++ was a version that we developed at UT. Basically, it took in 3 inputs, right? It took in the application that I just showed you. It took in those functional units written by RTL experts and microarchitectural template, and then it would go and produce this, effectively this particular piece of, it was Verilog that we would synthesize and place and route for the FPGA, and it would just generate this, and that would run this application using these functional units in this microarchitectural template. So the output was highly throughput optimized. There was cycle by cycle multi-threading, so single instruction per thread, no bypass, no interlocks. Well, as I said, the intention was to make the hardware as simple as possible, and it could be highly pipelined. And you can compose various engines together in a variety of ways. So we could actually go and, this functional unit could go and effectively be another engine that was generated in a previous, by the same tooling, right? So this is kind of what we had before. Quality of results was quite good. The intention was that it was very easy to program this. My student who did this, Mason Lavasani, was able to go and generate lots of applications in not very much time. What we did is we went and compared against the best best performing and resource efficient solutions that we found in the literature. So these are the applications we ran. This is basically the relative area. Sometimes we were a little lower, sometimes a little higher. On average, we were about 10% higher, but the performance was always at least as good using this particular approach. The Gorilla++ also had an automatic design space exploration component. This would be done by essentially instrumenting the output of the tool. There were various counters all over the place, and the tooling could then go and we would perform runs. We had tooling that would then go and take the output of those runs, especially along those telemetry counters, and would actually automatically go and optimize. So in this particular case, for this small application, this is you can see we started the baseline. This is how much back pressure there was in this particular histogram engine. At some point, we get to to a reasonable amount of back pressure. We balance the back pressure for the histogram engine and the cache controller, and we get the performance. We get to a high throughput at a specific area, right? So just want to show this as an example. This is as of how we can automatically go and tune the particular hardware that we generate. So we also been working in this thing called DO GPU. This is domain optimized GPU. This is a soft GPU that's based on the FGPU work. That's prior work from another group. But fundamentally, what we did is we took that DO GPU, the FGPU, and we went and allowed us to go and specialize macro units and specialize scalar functional units. So we went and specialized. We also improved a bunch of other things, but fundamentally, we allow for specialization here. That specialization now potentially gives us significant, allows us to be pretty efficient. This is speed up using an S10-210 over an NVIDIA T4. These two parts are roughly the same in area. And sometimes we're faster, sometimes we're slower. This is really just, there's a lot more work to be done here as well, but this is just to show that an overlay is not necessarily going to be killed by a GPU. And we think that we're kind of in the same ballpark. And these are all, we basically used NVIDIA's libraries to go and generate these applications. So the intention was to try to get as good as possible against their particular implementation. There are a bunch of things that we didn't, we did select problem sizes based on our overlay rather than GPU, so that's our advantage, but we didn't normalize anything. So there's a lot of cases where the GPU has more memory bandwidth, for example. We didn't penalize the GPU for that. This is just kind of straight comparison. And again, we want to do more work in this area. All right, so now let's go over to the Crossroads overlays and talk a little bit about what we're trying to do here. So we all know that processor development is non-trivial. I mean, there are big companies like Intel whose main job in life is to develop processors. And so, how you go and do the appropriate trade-offs between performance, area, power, and integration, right? These are all things that, fundamentally, actually, before I continue, I've been talking really quickly. Does anyone have any questions? Okay, so I'll keep going. And again, just feel free to interrupt me if you have any questions. So really fundamentally, we want to, there's a lot of trade-offs that occur when we're going and developing processors, and exploration is expensive. So can we go and generate overlays? And these overlays now become, everything that I talked about in the past in terms of Magilla and Gorilla++, they did not have instructions. That was just generating a specialized finite state machine for the particular application that was written. So there was no configurability there. So can we go and generate overlays? So there's common structures. There's kind of a skeleton. You can think of it as a microarchitecture skeleton. Instruction fetch, decode, data fetch, write back. Kind of the standard things you do in a processor. Did someone just say something? Okay. All right, and there, caches and data paths are all part of that. So we can specialize in a few different areas, right? We can specialize functional units, we can specialize the memory structures, data types, and WISN, and by in corollary, kind of the NOC here. And we'd like to be able to automatically tune all of this, right? So that's kind of the intention of these crossroad overlays. So the Gorilla++, is where we started. We're moving over to so we named this particular overlay project Primate. And what we're doing here is we're basically taking the same things, application, but now instead of taking a single application, we're taking multiple applications, right? So in the Gorilla++ strategy, we went and took, a single application. Now we're taking multiple applications. We're also going to take partial inputs, right? So it may be that some of the inputs that were originally, put into these functional units, maybe we have constants for them that actually can potentially improve our performance and specialize the functional units. And then the same microarchitecture template. So we went and added these two components, multiple applications and the partial inputs. And so the goal here is to take the multiple applications that we put in and automatically generate an overlay that can execute all those applications. Now, the overlays that we generate, some may favor one application over another, right? And so we need to actually weigh what application is more important. But that's really the intention, is to automatically generate an overlay that can run all of these set of applications based on some criteria of run, right? So and this is really the Primate tooling that we're proposing here. So this allows us to do program development. I can go and modify. So once I get this overlay, basically I get a compiler that can go and compile that overlay onto the applications onto the overlay as well. Once I have this, I can go and do my program development without having to go through the synthesis, place, and route again to run on a real FPGA. I can do my program development, change things and so on. Obviously, if I need to add more functional units, I need to, change the hardware. I'm going to have to go through synthesis, place, and route. But we believe that you can do a lot of work here if you get this right. And you can write completely new programs that could be targeted to this. Again, it may not be fully optimized, but you can write new programs for this, right? So that this is kind of the high level goal here. So the overlays enable a family solutions rather than having one processor. You think, what can I buy from Intel? Well, I can buy Atoms and I can buy Xeons. And within a particular Xeon family, the kinds of different parameters I have is number of cores, amount of cache, that kind of thing. But I want to buy a processor that's better at debug, or I want to buy a processor that eliminates, a lot of the overheads. I don't need any cache for this application. I'm going to go to memory all the time anyways. Just throw away the cache, give me more cores. I can't do that. Right. Fundamentally, because it's so expensive to develop each one of the ASIC processors, I'm kind of limited. Here, we believe that we can actually build a family of solutions that can be run, concurrently or different phases, right? So all intended to run the same source code. We may have different instructions to be able to optimize more, right? But the intention is to all run the same source code. But different specialized versions can minimize time to solution. So imagine a debug version that's got a tremendous amount of instrumentation. It's going to run slower because we're going to be dumping out traces. It's going to have, perhaps less compute capability, so on. But I can build a debug version that can go and look at a lot more of what's going on in the processor than a standard processor could. I can have high flexibility versions. I can add additional functional units. I can put in more generality, which allows me to kind of operate to debug and develop while not having to go back to the synthesis, place, and route. I can have auto-tune versions. Let's say I need something that, really need to minimize area. don't care so much about performance and power, I can do that. Likewise, I can trade off, on a variety of different metrics. I can have specialized requirements. I mean, say, look, I want a highly reliable version, duplicate my functional units, go and add additional security capabilities, and so on. These are things that can also be generated, from this tooling, or that's the intention. It's not working, we don't have this right now, but this is the intention. And then we can do highly specialized non-overlay version. We can go back to the original Gorilla++ kind of output, where we just eliminate all of the programmability and get to the final, very, very powerful solution. So I think for development, you can see that this is a really nice way for us to be able to go. If we can go and generate a variety of different applications, all still running the same source code, if I can generate a variety of different overlays, then fundamentally I can go and have different kinds of overlays for different phases of my total solution time. We can do the measurement-driven automatically generated improvements, that was present in Gorilla++. And then how and when to switch between these and how to optimize is a rich area of study. And that's really what we're proposing to do. And we can also, potentially have specialized hard logic to improve the overlays. That's where we intersect with RV3. And I'll talk a little bit more about that in the future. So Primate code, this again is very similar to, this is the kind of assembly which is, we're going to look at as, we're going to view this as assembly to begin with. We'll write in this to begin with, but, fundamentally this is the original Gorilla++ code. It's going to be standard C sequential code that calls functional units, right? So then what winds up happening is we're the first template that we're going to be using, this microarchitectural template that we used back in the Gorilla++ days. We're going to have per cycle multi-threading in VLIW. So this allows us to go and effectively use this pipeline, use these functional units efficiently, because what we'll do is we'll be essentially allowing multiple threads to be using these functional units, on a cycle by cycle switch kind of basis. Again, we'll be using VLIW instructions where there's no inter-instruction dependencies, and each functional unit is activated up to once per instruction. So fundamentally, these are all, you can, request the functional unit to do something. You can do that across all four, but you can't go and say, I'm going to use A twice in one instruction, right? This is just to avoid a hardware structural hazard. The threads are going to be independent of each other. They can interact with each other through a functional. You can imagine if I have a counter that counts different threads of a network flow. If all of the packets are from the same flow, we can go and ask that counter functional unit to increment that particular flow counter for each one of them, right? And of course, then we're going to be bottlenecked by that. But if we have a flow counter counter that has a throughput of 1, we won't be bottlenecked by that, right? So that would allow us to be able to do that count for every cycle. And of course, multi-threading, it basically allows us to use this whole pipeline more efficiently. But what we're going to do is we're going to ensure that all active functional units for each instruction is complete before we go to the next one. Again, this is really intended to avoid us having to do automatic or hardware detection of where there are dependencies, right? So this is just really to simplify the hardware implementation. There's no reason for us to not go and be more aggressive there, but to start with, this is what we'll do. So what will these instructions for the Primate overlays really look like? Well, the model is really to take the Gorilla++ finite state machine, to a program composed of these VLIW instructions, and the way independent threads executing the same program, which we said before. But this is a particular example of a VLIW instruction for for 4 functional units. This is a typo, where I'm going to basically specify kind of opcodes for the opcodes and arguments for the pre stages, and then the 4 functional units, and then the post, right? It's going to be very simple to begin with. We're not going to try to compress in the very early version. I mean, instructions, as we all know, are oftentimes compressed to some degree. We'll just lay it out as, you can think of this as kind of a microcode version, and then fundamentally use this as our initial set of instructions. The length is obviously going to be dependent on the application and it turns out the overlay, right, that we're going to be generating for it. And then the scheduler will basically dispatch the VLIW instructions from multiple threads simultaneously. So this is, our approach is going to be using spiral plus the Gorilla++ seeds. The Gorilla++ is intended to go and be more general, allow us to tackle many domains. we're Franz, James, and I and our students are really going and talking about, what's the right application space that we can apply Spiral kinds of capabilities into this flow. Spiral is well known to have some HPC, FFT, and other kinds of applications and machine learning. And so we're discussing how to essentially incorporate the Spiral capabilities in, but also still continue to develop on the original kind of simplified approach that we're using on this side, but it's going to be more general because this requires much less work than building each one of these particular Spiral domains. There's going to be a lot of R3 intersection. So fundamentally, the question we've already started asking ourselves is what should be hardened, right? This is going to require some research, but things that are kind of coming up are thread scheduler, instruction front end, kind of fetch decode, hardware register banks, hardened functional units like a load store unit, potentially caches, branch logic, and so on. So you can think of everything that you see common in an overlay that's in a processor. We can potentially go and do that. Now, obviously, things are going to have to be configurable here, right? If we have a variable, each particular different overlay may have a different instruction width and how you interpret that instruction. We may have our fetch unit's going to have to be configurable for that, and the decode, of course, as well. But we think that these are areas that we really could go and do some interesting hardening, which would be on that base die and allow us to be much more efficient in these areas. One thing that we do need to account for is data movement. I'll show you a slide on that here. So one of the issues that we've, all FPGA developers have is really how do you go when you have hardened components and you want to be close to certain areas, for instance, your PCI or Ethernet lanes. You have to manage your data movement and make sure that the movement through the FPGA and where you place your actual logic is good relative to where the data is coming from and where the data is going to. So imagine if this is my base die, this is the hardened logic, and this is the FPGA logic, which is we're talking about the green logic, which is the pre-logic, and the post-logic, and the blue logic, which are the functional units that we're trying to optimize for. We imagine if we lay these two on top, what we really like to be able to do is we would like to be able to not necessarily have the reconfigurable logic always have to be in kind of close proximity to where the source the data will be generated from and where the data is going to flow to. In this particular case, we're showing things are nicely laid out. But imagine if A needs certain special it uses certain DSPs that may need to be spread out a little bit more across the board. Having the ability to be able to communicate from one point to another could allow us to use the FPGA fabric much more efficiently. So one of the things we're hoping for is that we'll be able to define a base die that essentially allows us to teleport from, let's say, from this particular point over to this particular point where there's another block of DSPs that we need. If we can use the NOC to be able to get there at low latency and relatively low power, that would be great, right? That would allow us to now go and be much more flexible about what's going on inside the FPGA and the layout of the FPGA relative to the resources that are in the FPGA, or potentially functional units or whatever that get embedded inside the base die. So this is an area of research, but we think that this going and defining what's in the base die and the appropriate NOC connectivity is going to potentially give us a lot of benefits. There's also an RV5. This is the kind of partial reconfiguration intersection where we think there's a lot of power here potentially. What if you rather than having to go and do a different overlay, you can go and swap out functional units. You could swap out different kinds of interconnects in the soft logic and so on. This would give us a tremendous amount of flexibility over time as well. Right. So we think that this is really a nice, rich area of research. One strategy, of course, is we generate different overlays, but by going and partially reconfiguring, as we go, we could potentially become much more efficient. Of course, one of the things that needs to be considered in all this is reconfiguration bandwidth versus data bandwidth in areas. So one of the things, partial reconfiguration requires bandwidth to go and load up that logic. load up that configuration for that logic that could be better used for moving data. So this is something that needs to be traded off and needs to be understood as we go and research this. So anticipated first year results. We're working with the Pegasus team in RV1. Right now during the summer we're not on weekly development cadence, but once the summer ends, we'll start that back up again. We've been looking at a fast multi-stream pattern matcher and a flexible protocol processor. These require fast compile times and high performance. So we're looking at these. We're also looking internally at potentially going and looking at other kind of network applications built out of the original Gorilla++ network processor that was a IPv4, IPv6 MPLS network processor. So we're looking at that as well. And we've been discussing on figuring out how to integrate with we call the monkey for a while. It's now called Primate integration for machine learning. So we're talking about that as well. Again, things are slower in the summer, but the hope is that we'll be able to come up with a strong path forward for the second year around machine learning with the Spiral team. So in conclusion, we believe that overlays are a promising way to improve time to solution. We want to go for better than software development. We think that by having appropriately instrumented processors with the right telemetry, we can actually do better than software development, and both for debug and for tuning. We think that we can get high performance from this, and we believe that we can really improve our development time, our time to solution on the development time. Correct tooling is required. This is what we're intending to build, but what this correct tooling will enable us to do is enable experts to officially contribute in their particular area, right? So this is a story that people have been talking about in domain-specific languages. Fundamentally, this is a domain-specific language, but building hardware for them. But we want the application expert to be able to go and write their applications very effectively. We want RTL experts to be able to contribute functional units. We want architects to be able to contribute those templates, right? So fundamentally, if we can basically, this tooling takes inputs from the right people at the right time, we believe that we can really improve our time to solution, improve our productivity. And we want to basically generate known patterns. One of the things that when I started this work, the Gorilla++ work with Mesam, I told them, look, if you think about all of the tricks that people play once that you learn in academia, you put to practice in industry, there's a few things to make hardware more efficient, right? We can do pipelining, we can do multi-threading, we can do offload, right? So there's a bunch of strategies that we take. What we're trying to do is we're trying to encapsulate as many of those strategies as possible into the tooling, right? And so we don't have to manually do it. We can have the tooling kind of apply these patterns. The right hardware structures and configurability are needed. That's our intersection with RV3 and RV5. We're really very excited about RV3 right now. I think configurability as we get more things running, RV5 is going to be very interesting as well. And we want to demonstrate on networking and machine learning applications. We have weekly meetings, and the summer again, because the students are either moving or in internships. We're every other week over the summer, but once the school year starts up again, we'll be weekly. But if anyone's interested in joining our meetings, please send me an email and we're happy to add you. All right. So that's the end of my talk. Any questions or comments?